Okay, so um, where we left off was we were saying that the emission of light depends on, sorry, emission of electrons uh, depends on whether the photon has enough energy to dislodge a single electron. And for this, we have what's called the threshold frequency of light. And the threshold frequency is just given by h nu, with nu being the threshold frequency. And that is equal to phi, or phi if you prefer, the Greek letter phi, which is their equivalent of a pH. And that's used as a symbol for the binding energy of the electron to the substance that originally owned it. So it takes a certain amount of energy to release an electron from any given substance. And if the energy of the incident light is equal to or greater than that binding energy, then emission of electrons will occur. If you want to know the threshold frequency, that's going to be phi over h. H being Planck's constant, and as we've seen before. So it's just a rearrangement of this equation here. The threshold frequency, if you want to know that, take the binding energy divided by Planck's constant. And basically any light with a frequency greater than the threshold frequency will cause emission of electrons. And the reason that we need this equation is because the binding energy will actually vary from one substance to another. Some substances, like the metals in, say, group 1 or group 2 of the periodic table, have very low binding energies, and it takes very little energy on the part of an incident photon to get them to spew out some electrons. Other substances have much higher threshold frequencies because they have much higher binding energies. So something like fluorine. You would probably have to hit fluorine with X-rays or maybe even gamma rays in order to get fluorine to give up any electrons. So it can vary quite a bit. Any photon energy beyond the binding energy goes into the kinetic energy of the electron. The electron released is known as a photoelectron because it's an electron that was released as a result of the action of light on the original substance. So that's a photoelectron. And so the Ke of the photoelectron, that is the kinetic energy of the electron that's being released from the substance, is just h nu of the photon that was incident on the substance minus the binding energy. Okay, so that makes sense. If you add more energy than you need to dislodge the electron, then the extra energy just goes into making the electron move away faster. And because of all of this, we conclude that light must have some properties of waves and some properties of matter. And this is what we mean by wave-particle duality. So light is neither entirely waves nor entirely particles. All right, so this brings us to section 7.3, that is atomic spectroscopy and the Bohr model. So atomic spectroscopy and the Bohr model. So the wave particle duality for light was really the first hint that not everything obeys Newtonian mechanics. And other small particles have also been discovered to have wave properties. And those would include things like electrons and protons and neutrons. And so atomic spectroscopy is the study of absorption and emission of electromagnetic radiation by atoms. So remember, EMR is electromagnetic radiation. And that's usually in the form of light or something related to light. When energy is absorbed by an atom, and energy can be absorbed by an atom in the form of heat or light or electricity. For example, it's often released as electromagnetic radiation. So an atom doesn't really have to absorb energy in the form of electromagnetic radiation in order to emit electromagnetic radiation. Even when an atom does absorb electromagnetic radiation, it often emits electromagnetic radiation of different wavelength and frequency from what was absorbed. Okay, so that's an interesting phenomenon. So some examples would be things like sodium vapor streetlights. Those are the yellow streetlights, or mercury vapor streetlights. Those are the white ones. Except actually there are some new LED type streetlights like the ones they just installed on Niagara Falls Boulevard that use a lot less energy. So we're going to be seeing a lot more of those in the future. But for now, most of them are still either sodium vapor or mercury vapor lights. And they work on the principles of atomic spectroscopy, where the atoms of sodium or mercury inside the light will absorb energy in the form of electricity, and they will then emit energy in the form of visible light. And for sodium, that one shade of yellowish orange light that they emit, that happens to be the only color of light that sodium vapor streetlights emit. Mercury vapor lights emit a lot of different colors, and those colors are spread across the visible spectrum sufficiently that the overall result that we see with our brains is white light. But again, because not every frequency or every shade of every color is present for the mercury vapor lights, it's a white light that still doesn't seem quite natural. It seems a little odd. Another example of that would be neon signs. Neon signs contain neon gas or other elements like krypton or xenon or helium. And actually, the only neon signs that actually contain neon are the red ones. The other colors, you know, like the green and the blue and the yellow, those are different gases. Helium is pink, for instance, I remember that. Hydrogen is kind of a purplish color, and so on. So different elements for different colors. And in the case of neon, the neon atoms in the tube will absorb energy again in the form of electricity, and then they will emit energy in the form of visible light, that familiar shade of red. Different substances emit different colors. You know, as I mentioned above, different substances emit different colors, which means that there must be something different about their atoms that results in them emitting electromagnetic radiation of different energies. Okay, the light emitted is often of more than one wavelength. So these basically let's say lights that work on these principles, they will often emit more than one color of light, like the mercury vapor lights. Mercury vapor lights emit a whole bunch of different colors. You know, probably a couple dozen different shades of the various colors in the visible spectrum. And so there must be multiple things going on within an atom that allows that. So there must be multiple things that are possible to go on inside the atom that would result in the release of more than one wavelength of electromagnetic radiation. And of course, what we from these various light sources, we only see one color because, again, our brains average together all of the colors we see. Our brains are not capable of separating the individual colors from each other. And on the other hand, the individual colors emitted can be separated with a grating or a prism. And once we do that, we can then observe them. So an emission spectrum is actually a series of colored lines and basically what you do is you take the light source that's emitting the light and you channel it through a prism or a grating, and then you project what's emitted from the prism or grating onto a screen or a background, and that way you can actually see a separate line for each color of light that's being emitted. And so an emission spectrum is a series of colored lines, and they're separate colored lines, and they will fall at certain wavelengths. And for most light sources, these lines are not continuous. If you're looking at the sun or an incandescent Edison style light bulb or some other object that's really hot, then you'll often get what's known as black body radiation. And that is a continuous spectrum of colors where all of the colors of the rainbow just bleed right into each other, and there are no gaps between the colors. But for most other light sources, like, say, mercury vapor lights, you will see a range of lines of various colors separated by nothing. And so these are known as discrete lines or separate lines. And what it means is that only certain colors of certain wavelengths are being emitted. So not every wavelength is being emitted. And these lines are always the same for a given substance. So if you see a certain pattern, you'll know that it must be mercury, or it must be sodium, or it must be potassium, or it must be neon, or whatever. But anyway, the pattern, the number of colors, and where they are is unique for each given substance. And so the spectrum, the emission spectrum, can actually be used to identify a given substance. One example of that is, say, the composition of a star in outer space. It's not really easy for us to go to that star and take a sample of it. It's kind of hot and kind of far away. So what we can do instead is take the light from that star with a really sensitive telescope and do an emission spectrum on it. And when we look at the different wavelengths of light that are being emitted by that star, we can actually determine what elements make up this star. So there's something about the structure of an atom that causes certain wavelengths to be emitted and certain other wavelengths not to be emitted. In, I think it was around 1900, well, not too long afterwards, Rydberg, Johannes Rydberg, was able to predict the wavelengths of the hydrogen spectrum. But unfortunately, he was unable to say why. He actually came up with an equation that explained the lines that were observed in the hydrogen spectrum. But oddly enough, he didn't know exactly what the terms in the equation meant because the structure of the atom had not been fully elucidated by that time. So his equation, which only worked for hydrogen, and oddly enough, even today, with all of the advancements we've made in science, even today, we can only predict the lines for hydrogen, not anything else. And it has to, and it's basically down to the electrons. Hydrogen only has one electron, and even that gets pretty complicated because of all the different places the electron can go. Even if you go to helium with 2 electrons, that extra electron adds so much complication that we are not able to do calculations like this for helium even now. But anyway, he predicted that 1 over the wavelength for each given line of hydrogen would correspond to what we call capital R, which is known today as the Rydberg constant, times 1 over some integer squared minus 1 over some other integer squared. And so R is 1.097 times 10 to the 7th inverse meters or per meter. He was able to calculate that. And M and N are positive small integers. But he didn't actually understand why that equation works. So that's the interesting part. It was up to Niels Bohr, who came along a few years later, to elucidate things. Niels Bohr modeled the atom with what are often called shells or orbits of electrons around the nucleus. And this is also sometimes known as the solar system model. As well as the Bohr model. Where you have electrons orbiting around the nucleus, much in the same way as you have planets orbiting around the sun. There are a couple differences, though. In the Bohr model of the atom is three-dimensional. The solar system is more or less two-dimensional because the planets are all in more or less the same plane. And also in the Bohr model, it's possible to have more than one electron per orbit, unlike the solar system where you only have one planet per orbit. Sometimes that planet might have one or more moons, but generally only one planet. You can have several electrons per orbit. Okay, according to this model, the shells or the orbits can only exist at certain distances from the nucleus for a given element. But if you look at a different element, the shells in that element will be different distances from the nucleus. The distance corresponds to energy. And energy increases as you move away from the nucleus. Actually, what it is the energy for the first shell of electrons right up near the nucleus is very negative energy. And the energies of the successive shells get less and less negative as you move out from the nucleus. And eventually, when you're an infinite distance away from the nucleus, you would reach an energy of 0. So actually, the energies do increase as you go away from the nucleus, but they're starting very negative and they're getting less negative until you finally hit 0. Okay. Okay, the distance current with increases away from the nucleus. Okay, so that's what I just said. The energy is very negative for the first shell, and it gets less negative and approaches zero as you move further and further out from the nucleus. The energy of each orbit or shell is fixed for any given element, or in other words, quantized. So the shell for the shells of electrons in an atom of any given element cannot move around. They are where they are, and they correspond to a certain amount of energy, and that's the way it is for that element. Bohr said basically that the orbits are stationary states. With a certain amount of stability. That's inexplicable. He is basically saying these electrons, which by all rights should get sucked into the nucleus because the electrons are negative and the nucleus is positive, they are attracted to each other, but they're stable where they are, a certain distance from the nucleus. And why that is, Bohr didn't know. But the problem with this, that if an electron is in a stationary state, they should not be able to emit radiation of any kind. Release of electromagnetic radiation requires a certain amount of instability. And so he theorized that emission of electromagnetic radiation can only occur when changing from one orbit to another. And that's known as a transition. So transition is when an electron changes from one orbit to another. And that's a transition, and that is when emission of or absorption of electromagnetic radiation can occur. So if the atom absorbs energy, the electron moves to an orbit farther from the nucleus. This is known as an excited state. It's unstable, as the word excited kind of implies, because when you're really excited, you're kind of unstable. You're jumping all over the place and bouncing off the walls. So that's definitely unstable. And that usually is followed very quickly by an emission of energy. where one of the excited electrons moves to an orbit closer to the nucleus. This could result in the atom returning to its normal state, which is known as the ground state, or it could result in the atom going to an excited state that's just maybe less excited than it was before. You know, a state of lower energy, but not as low as the energy originally was. And there's a figure about this on page 289. Figure 7.11 that shows that in better detail than I can. So one thing that's a little, well, one of the ways in which electrons are weird is that the electrons in the Bohr model of the atom can only exist in one of these orbits. They cannot exist in transition from one orbit to another. So it's not actually the case that an electron moves from the first shell in the atom to the second shell. Essentially, what supposedly happens is the electron basically ceases to exist in the first shell and immediately pops up in the second shell. So there's really no transition as such. The electron just basically disappears in one place and appears in another. Okay. And the energies of the transition lines, or the energies of the lines in the emission spectrum, rather, are equal to the difference in energies between the states or orbits involved in the transition. Just like. Okay, so lower energy just means that the orbits are closer together. So if the electron transitions from, say, the third shell down to the second shell, that's going to result in a line with a wavelength that has relatively low energy. If the electron drops, say, from the sixth shell down to the first one, that's going to result in a line with a wavelength that corresponds to a very high energy. The Bohr model actually was a huge step forward in explaining the behavior of atoms, but it didn't answer all the questions. There are some that are still outstanding. Well, there's some that are still outstanding even today. And we'll pick up there next time with the next section, which is 7.4. But until then, I'll see you later.